What are the fundamental concepts of quantum computation and quantum information? How did these concepts develop? To what uses may they be put? How will they be presented in this book? The purpose of this introductory chapter is to answer these questions by developing in broad brushstrokes a picture of the field of quantum computation and quantum information. The intent is to communicate a basic understanding of the central concepts of the field, perspective on how they have been developed, and to help you decide how to best approach the rest of the book. Our story begins in section 1.1 with an account of the historical context in which quantum computation and quantum information has developed. Each remaining section in the chapter gives a brief introduction to fundamental concepts from the field: quantum bits or qubits, quantum computers, they don't exist yet, quantum gates and quantum circuits, quantum algorithms, experimental quantum information processing, and quantum information and communication. Along the way, illustrative and easily accessible developments such as quantum teleportation and some simple quantum algorithms are given, using the basic mathematics taught in this chapter. Quantum computation and quantum information is the study of the information processing tasks that can be accomplished using quantum mechanical systems. So what are those tasks? What can you accomplish with a quantum mechanical system that you can't accomplish with a traditional system? Sounds pretty simple and obvious, doesn't it? Like many simple but profound ideas, it was a long time before anybody thought of doing information processing using quantum mechanical systems. To see why this is the case, we must go back in time and look in turn at each of the fields which have contributed fundamental ideas to quantum computation and quantum information. What are these fundamental fields? Quantum mechanics, computer science, information theory, and cryptography. As we take our short historical tour of these fields, think of yourself first as a physicist, then as a computer scientist, then as an information theorist, then as a cryptographer, and finally a baggie, in order to get some feel for the disparate perspectives which have come together in quantum computation and quantum information. Our story begins at the turn of the 20th century when an unheralded revolution was underway in science. A series of crises had arisen in physics. The problem was that the theories of physics at the time, now dubbed classical physics, were predicting absurdities such as the existence of an ultraviolet catastrophe involving infinite energies or electrons spiraling inexorably into the atomic nucleus. At first, such problems were resolved with the addition of ad hoc hypotheses to classical physics. But as a better understanding of atoms and radiation was gained, these attempted explanations became more and more convoluted. The crisis came to a head in the early 1920s after a quarter century of turmoil and resulted in the creation of the modern theory of quantum mechanics. Quantum mechanics has been an indispensable part of science ever since and has been applied with enormous success to everything under and inside the sun, including the structure of the atom, nuclear fusion in the stars, superconductors, the structure of DNA, and elementary particles of nature. What is quantum mechanics? Quantum mechanics is a mathematical framework or set of rules for the construction of physical theories. For example, there's a physical theory known as quantum electrodynamics, or QED, which describes with fantastic accuracy the interaction of atoms and light, or photons. QED is built up within the framework of quantum mechanics, but it contains specific rules not determined by quantum mechanics. The relationship of quantum mechanics to specific physical theories, like quantum electrodynamics, is rather like the relationship of a computer's operating system to specific software. The operating system sets certain basic parameters and modes of operation, but it leaves open how specific tasks are accomplished by the applications. The rules of quantum mechanics are simple, but even experts find them counterintuitive. And the earliest antecedents of quantum computation and quantum information may be found in the long-standing desire of physicists to better understand quantum mechanics. Let me repeat, the earliest antecedents, or the earliest predecessors, or the earliest reasons for wanting to learn about quantum computation and quantum information comes from quantum mechanics and wanting to understand that better. The best known critic of quantum mechanics was Albert Einstein, and he went to his grave unreconciled with the theory that he helped invent. Generations of physicists since have wrestled with QM in an effort to make its predictions more palatable. One of the goals of quantum computation and quantum information is to develop tools which sharpen our intuition about quantum mechanics and make its predictions more transparent to human minds. For example, in the early 1980s, interest arose in whether it might be possible to use quantum effects to signal faster than light. So can you transmit information faster than the speed of light? A big no-no according to Einstein's theory of relativity. And this is important for you, 𝗏𝗏𝗧𝗏. I asked you about this yesterday and you didn't have an answer, so now you're going to have an answer, all right? The resolution of this problem turns out to hinge on whether it is possible to clone an unknown quantum state. That is, to construct a copy of a quantum state. That's for everybody. Can you copy or clone an unknown quantum state so you don't know what its linear combination is? If cloning were possible, then it would be possible to signal faster than light using quantum effects. Isn't that crazy? So if cloning were possible, you could signal information faster than the speed of light. However, cloning is so easy to accomplish with classical information. Look at the words in front of you or our YouTube chat. It turns out not to be possible in quantum mechanics. This is called the no cloning theorem. All right? Remember that. The no cloning theorem, which was discovered in the early 1980s. I was born. This theorem, the no cloning theorem, and by the way, in math, when we say theorem, that means it's been proven. So it's like as good as a fact, in case you'd ever heard that word before, theorem. It is one of the earliest results of quantum computation and quantum information. Many refinements of the no cloning theorem have since been developed. And we now have conceptual tools which allow us to understand how well a necessarily imperfect quantum cloning device might work. These tools, in turn, have been applied to understand other aspects of quantum mechanics. A related historical strand contributing to the development of quantum computation and quantum information is the interest dating in the 1970s of obtaining complete control over single quantum systems. Applications of quantum mechanics prior to the 1970s typically involved a gross level of control over a bulk sample containing an enormous number of quantum mechanical systems, none of them accessible. For example, superconductivity has a superb quantum mechanical explanation. Anybody know much about superconducting? Superconductivity, anybody? Any Cooper pair fans in the building? Any Josephson junction people? Because a superconductor involves a huge, compared to the atomic scale, quantum scale, a huge sample of conducting metal, we can only probe a few aspects of its quantum mechanical nature, with the individual quantum systems constituting the superconductor remaining inaccessible. Systems such as particle accelerators do allow limited access to individual quantum systems, but again, no control over those systems. Since the 1970s, many techniques for controlling single quantum systems have been developed. For example, methods have been developed for trapping a single atom in an atom trap. This reminds me of an ion trap, right? Isolating it from the rest of the world and allowing us to probe many different aspects of its behavior with incredible precision. So trapping a single atom in an atom trap. The scanning tunneling microscope has been used to move single atoms around, creating designer arrays of atoms at will. Electronic devices whose operation involves the transfer of single electrons have been demonstrated. Why all this effort to attain complete control over single quantum systems? Why? Why are we doing this? What's the point? Setting aside the many technological reasons and concentrating on pure science, the principal answer is that researchers have done this on a hunch. Often the most profound insights in science come when we develop a method for probing a new regime of nature. For example, the invention of the radio astronomy in the 30s and 40s led to a spectacular sequence of discoveries, including the galactic core of the Milky Way galaxy, pulsars, and quasars. Low temperature physics has achieved its amazing successes in finding ways to lower the temperature of different systems. In a similar way, by obtaining complete control over quantum systems, we are exploring untouched regimes of nature in the hopes of discovering new and unexpected phenomena. We are just now taking our first steps along these lines. And already a few interesting surprises have been discovered in this regime. What else shall we discover as we obtain more complete control over single quantum systems and extend it to more complex systems? Now, if that doesn't get you excited, I don't know what will. This is the most interesting thing in science. I mean, how incredible is that to think about quantum mechanical effects and what can we do? Like, how do we use them? How can we harness them to do what we want? How do we bend the universe at its will, at our will, to control matter and all of its power? You know, that's the question of quantum computing, and it's very, very important. Quantum computation and quantum information fit naturally into this program. Quantum computation fits naturally into this program. They provide a useful series of challenges at varied levels of difficulty for people devising methods to better manipulate single quantum systems and stimulate the development of new experimental techniques and provide guidance as to the most interesting directions where we'll experiment. Conversely, the ability to control these systems is essential if we want to harness the power of quantum mechanics for quantum computation. Despite this intense interest, efforts to build quantum computers have resulted in modest success to date. Small quantum computers capable of doing a dozen operations on a few qubits represent the state of the art in quantum computation. Now, of course, nothing has changed since this publication. That still is the state of the art, even though the numbers are a little bigger. And remember, this was written 10 years ago, maybe some more. Experimental prototypes for doing quantum cryptography, a way of communicating in secret across long distances, have been demonstrated and are even at the level where they may be useful for some real-world applications. However, it remains a great challenge to physicists and engineers of the future to develop techniques for making large-scale quantum computing a reality. A great challenge. Let's turn our attention from QM to computer science, another great intellectual triumph of the 20th century. This is really interesting stuff. Are you guys ready? This is going to help you in general, in life, okay? The origins of computer science are lost in the depths of history. Cuneiform tablets indicate by the time of Hammurabi, almost 2000 BC, the Babylonians had developed some fairly sophisticated algorithmic ideas. And it is likely that many of those ideas date to even earlier times. The modern incarnation of computer science was announced by the great mathematician, Alan Turing, in the remarkable 1936 paper. Alan Turing basically invented computing and computer science. Turing developed in detail an abstract notion of what we now would call a programmable computer, a model for computation now known as the Turing Machine. Turing showed that there's a universal Turing machine that can be used to simulate any other Turing machine. Furthermore, he claimed that the universal Turing machine completely captures what it means to perform a task by algorithmic means. That is, if an algorithm can be performed on any piece of hardware, like a modern PC or your iPhone, then there's an equivalent algorithm for a universal Turing machine which performs exactly the same task as the algorithm running on that computer. This is known as the Church-Turing thesis. Alonzo Church was another pioneer. And it says that the equivalence between the physical concept of what classes of algorithms can be performed on some physical device, that there's an equivalence of that with the rigorous mathematical concept of universal Turing machine. The broad acceptance of this thesis has laid the foundation for the development of a rich theory of computer science. So we can read about the 𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗪𝗧𝗙�ึ𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩𝒩 I think you should read about the halting problem. And I would suggest you read Michael Sipser's books. Sipser, MIT professor of computer science. Not long after Turing's paper, the first computers constructed from electronic components were developed. John von Neumann developed the simple theoretical model for how to put together a computer, like a universal Turing machine. Hardware developed took off in 1947. Remember, 1947, when Shkreli, and also Bardeen and Bertin, developed the transistor. 1947. We're still using these things. So maybe quantum's time is coming. Maybe quantum's time is coming. But will it be this decade or next decade or the decade next? We don't know. Computer hardware has grown at an amazing pace since. Gordon Moore's law in 1965 states computer power will double for constant cost every 2 years. Moore's law has held true since the 60s. It's kind of crazy, right? But most observers expect that this dream run will end sometime in the next 2 decades. Or will it? Or will it? Maybe it's getting faster. Thank you, NVIDIA. Conventional approaches to the fabrication of computer technology are beginning to run up against fundamental difficulties of size. Quantum effects are beginning to interfere in the functioning of electronic devices as they're made smaller and smaller. What does that mean? Well, how big is a transistor? Do you guys know? How big is a transistor? 30 nanometers? What do you guys think? So there's this length, and then there's this length. This is called the channel width. And remember, these things are also embedded in lattices, so you can't really exactly, kind of, so I don't know, you could say 7 nanometers. What's the distance between a carbon-carbon atom? The channel width is a little bit different. That's more like 30 nanometers. Anybody know? Remember, all of these stocks are based on this. So this is, what, 150 picometers, roughly, which is 1.5 angstroms, which is 0.1 nanometers. So when they're talking about quantum effects, right, these transistors for scale, I don't know, let's see, let's do this we can do this, right? For scale, what would they look like? Well, there would be 70 of these, right? How many do we have to do? Pop quiz. There's 4. What is that, 32? Here's 64 now. And 6 more for good measure. So we're getting close to the size of an individual atom, right? This right here is an individual atom. This right here is a whole transistor. We're not far away, are we? So the quantum effects are starting to take over. As we get smaller, well, that famous Schrodinger concept of physics and basic chemistry and physics is wave-particle duality, right? In the macroscopic world, I throw a baseball at you, it certainly feels like a particle. This is 𝗥𝗢𝗓𝗏's head. That's a stock quote of IonQ some point in the future. So what's particle wave duality? Well, at macroscopic levels, objects behave like particles. But as we get smaller and smaller, they tend to start behaving like waves. So we're getting smaller and smaller to the point where waves exhibit quantum mechanical effects, and those effects are starting to interfere with how we build these tools. One possible solution to the problem posed by the eventual failure of Moore's law is to move to a different computing paradigm. Which paradigm is that? We're talking about quantum computing. That could be a solution to the eventual failure of Moore's law, but it may not be the only solution. It's not clear that we need to pass Moore's law for certain things. So keep that in mind. It certainly doesn't feel like we need it for a web browser. One such paradigm is provided by the theory of quantum computing, which is based on the idea of using quantum mechanics to perform computations instead of classical physics. It turns out that while an ordinary computer can be used to simulate a quantum computer, and just for you guys, I'm going to start doing that. I want to show you how it works. It appears to be impossible to perform the simulation in an efficient fashion. This is where it gets really interesting. It's impossible to perform the simulation in an efficient fashion. What does that mean? The quantum computers offer an essential speed advantage over classical computers, but only in certain things and only in certain ways. So take that with a grain of salt first. This speed advantage is so significant that many researchers believe that no conceivable amount of progress in traditional classical computation like NVIDIA and Intel none of it would be able to overcome the gap between the power of a classical computer and the power of a quantum computer. The devil's in the details. We have to, every time somebody gives us something like that, some hard assumption, we gotta accept it in a temporary space in our mind, but still turn it around and be a little cynical and skeptical and poke some holes at it and see what we think of it after we do that. What do we mean by efficient versus inefficient simulations of a quantum computer? As the Rigetti CEO once famously said, what do you mean by useful? What does useful mean to you? Many of the key notions needed to understand this question were invented way before quantum computers even the idea ever came up. The idea of efficient or inefficient algorithms was made mathematically precise by a field called complexity or computational complexity. This is not something that's taught in high school. In fact, it's usually not even taught in college. Roughly speaking, an efficient algorithm is one which runs in time polynomial in the size of the problem solved. Okay, you know what a polynomial is. In contrast, an inefficient algorithm requires super polynomial time. Usually we call that exponential time. What was noticed in the late 1960s and early 1970s was that It seemed as though the Turing machine model of computation was at least as powerful as any other model of computation, in the sense that a problem which could be solved efficiently in some model of computation could also be solved efficiently in the Turing model, by using the Turing machine to simulate the other model of computation. This observation was codified into an even stronger form of the Church-Turing thesis. Any algorithmic process can be simulated efficiently using a Turing machine. The key strengthening in this strong form is the word efficiently. If the strong form is correct, then it implies that no matter what type of machine we use to perform our algorithms, that machine can be simulated efficiently using a standard Turing machine. This is an important difference because it means that for the purposes of analyzing whether a given computational task can be accomplished efficiently, we may restrict ourselves to the analysis of the Turing machine model of computation. But here comes a challenge. One of the challenges comes from the field of analog computation or analog computing. This is popular in the 80s and may very well have a big resurgence. So think about analog computing and something called probabilistic computing and adiabatic computing. There's more than one way to think about computing. Quantum computing isn't the only way about thinking about new forms of computing. In the years since Turing, many different teams of researchers have noticed that certain types of analog computers can efficiently solve problems believed to have no efficient solution on a Turing machine. How is that possible? At first glance, these analog computers appear to violate the strong form of the Church-Turing thesis. That's true. Unfortunately for analog computation, it turns out that when realistic assumptions are made about the presence of noise in the analog computers, their power disappears. They cannot efficiently solve problems which are not efficiently solvable on a Turing machine. This lesson that the effects of realistic noise must be taken into account in evaluating the efficiency of a computational model was one of the great early challenges of quantum computing, and still is. A challenge successfully met by the development of a theory of quantum error correcting codes. This was the Willow announcement was so important. And fault-tolerant quantum computation. So unlike analog computation, quantum computation can in principle tolerate a finite amount of noise and still retain its computational advantages. The first major challenge to the Church-Turing thesis arose in the 1970s, when Solovay and Strawson showed that it is possible to test whether an integer is prime or composite using a randomized algorithm. So this is pretty neat. If you want to learn this algorithm, you should check it out, the Solovay-Strawson test for primality. Randomness was an essential part of the algorithm. The algorithm did not determine whether a given integer was prime or composite with certainty, but it could determine its probability. If you repeat this test a few times, you're able to determine with near certainty whether a number is prime or composite. So the reason this is important is that at the time it was proposed that there was no deterministic test for primality, and there hasn't been one since. So it seemed that computers that could use random numbers would be able to efficiently perform some tasks where there's no efficient solution for a conventional deterministic Turing machine. This discovery inspired research for more randomized algorithms, maybe even some in finance. Randomized algorithms pose a challenge to the strong Church-Turing thesis, suggesting that there are efficiently soluble problems which nevertheless cannot be efficiently solved on a deterministic Turing machine. We can modify the strong Turing thesis by weakening it, and we can say that any algorithmic process can be simulated efficiently using a probabilistic Turing machine. Okay, another modification. Won't it turn out some years later that yet another model of computation comes out and it's able to efficiently solve some problems that are not efficiently solved within this one? Is there any way we can find a single model of computation which is guaranteed to be able to efficiently simulate any other model of computation? In 1985, David Deutsch, who I strongly recommend you read his works, asked whether the laws of physics could be used to derive an even stronger form of the thesis. Instead of adopting ad hoc hypotheses, Deutsch looked to physical theory to provide a foundation for Turing, and such that it would be as secure as the status of that physical theory. Deutsch attempted to define a computational device that would be capable of efficiently simulating an arbitrary physical system. Deutsch invented the concept of a quantum computer. A lot of people say it was Feynman. Because the laws of physics are ultimately quantum mechanical, Deutsch considered computing devices based on quantum mechanics. These devices, which were quantum analogs of the machines defined 49 years earlier by Turing, led to the modern conception of the quantum computer. It's not clear whether Deutsch's notion of a universal quantum computer is sufficient to simulate any arbitrary physical system. Proving or refuting this conjecture is one of the greatest open problems in the field of quantum computing. It is possible that some effect of quantum field theory, or even some more esoteric effect in string theory, quantum gravity or something else, may take us even beyond Deutsch, giving us yet a more powerful model for computation. We just simply don't know. We still have to figure out quantum after all. What Deutsch's model of a quantum computer did was enable a challenge to the strong form. Deutsch asked whether it's possible for a quantum computer to efficiently solve computational problems which have no efficient solution on a classical computer, even a probabilistic Turing machine. You asks the important question. I thought it was Feynman who was first. They were sort of contemporaneous. The Beginning of Infinity, the excellent book. He constructed a simple example suggesting that indeed quantum computers might have computational powers exceeding those of classical computers. This remarkable first step taken by Deutsch was improved in the subsequent decade, culminating in Peter Shor's 1994 demonstration. This was the biggest event in quantum computing, other than maybe, its discovery. Peter Shor's 1994 demonstration. If you want to know anything about quantum, you have to know this. It's the very basics, right? Two enormously important problems, the problems of finding the prime factors of an integer and the discrete log problem, could be solved efficiently on a quantum computer. And this is good and bad. This is the only problem to this date, in my opinion, of importance that could actually be solved on a quantum computer. This attracted widespread interest because these two problems were still widely believed to have no efficient solution on a classical computer. Just try to factor a 200-digit number. Shor's results are a powerful indication that quantum computers are more powerful than Turing machines, even probabilistic Turing machines. Further evidence in the power of quantum computers came in 1995 when Grover showed that another important problem, conducting search through unstructured search space, could also be sped up. It was not as spectacular of a speed up as Shor's, but search-based methodologies are pretty exciting. I would put Shor's algorithm as the virtually only important part of quantum computing. So at the same time, and this is Yu's question from our chat, at the same time Shor and Grover's algorithms came out, many people were developing an idea that Feynman suggested in 1982, same time as Deutsch. Feynman had pointed out that there seemed to be essential difficulties in simulating quantum mechanical systems on classical computers, and suggested building computers based on the principles of quantum mechanics would allow us to avoid those difficulties. In the 90s, a lot of researchers started to do this and showed it is possible to use quantum computers to simulate systems that have no efficient simulation on a classical computer. It is likely that one of the major applications of quantum computers in the future will be performing simulations of quantum mechanical systems too difficult to simulate on a classical computer, a problem with profound scientific and technological implications. So I actually would somewhat disagree with that. Some scientists, of course, would love to perform some quantum simulations, but not everyone agrees that that would be a powerful or interesting market for commercial quantum computers. It's very exciting scientifically, but it's probably not very exciting commercially. Scientific software, especially theoretical scientific software, probably won't sell very well. So here's the important question. What other problems can quantum computers solve more quickly than classical computers? The answer is that we don't know. Coming up with good quantum algorithms seems to be hard. A pessimist might think that's because there's nothing quantum computers are good for, other than the applications already discovered. I don't know if that's true, by the way. We take a different view. Algorithm design for quantum computers is hard because designers face two difficult problems that we don't have in classical computers. First, our human intuition is in the classical world. If we use that intuition, then all the ideas we come up with are classical ideas. So we have to turn off our classical intuition and use the quantum effects to achieve what we want. It's interesting that, or to be really interesting, it is not enough to design an algorithm that's quantum mechanical. It has to be better than the classical algorithms. So it's possible you could find an algorithm that takes or uses quantum mechanics, but you still have to be superior to the classical one. So it's very, very difficult to create quantum algorithms, it seems. More broadly, we can ask if there are any generalizations we can make about the power of quantum computers versus classical. What is it that makes quantum computers more powerful than classical, assuming that this is indeed the case? What class of problems can be solved efficiently in a quantum computer, and how does that class compare to the class of problems that can be solved efficiently in a classical? One of the most exciting things about quantum computation and quantum information is how little is known about the answers to these questions. It's a great challenge for the future to understand these questions better. All right, let's switch our history to information theory. At the time computer science was exploding in the 40s, another revolution was taking place in understanding communication. In 1948, Claude Shannon published a remarkable pair of papers laying the foundation for the modern theory of information and communication. Perhaps the key step by Shannon. So Shannon said that to mathematically define the concept of information, he actually did that for the first time ever. In many mathematical sciences, there's a lot of flexibility of choice in these fundamental definitions. How do you define the information, the idea of information? There are, of course, several possibilities. And Shannon came up with a set of ideas that were definitely the most fruitful, which led to a lot of deep results and theory with rich structure, and a lot of accurate real-world communication problems were solved. His interest is in two key questions related to the communication of information over a communications channel. What resources are required to send information over a communications channel? So telephone companies need to know how much information can we actually send over the cable. And the second question is, can information be transmitted in a way so that it's protected from noise in the communications channel? So let's talk about information theory because it's important to quantum computing, okay? At the same time computer science was exploding in the 1940s, another revolution was taking place in our understanding of communication. In 1948, Claude Shannon published a remarkable pair of papers laying the foundation for the modern theory of information and communication. Perhaps the key step taken by Shannon was to mathematically define the concept of information. In many mathematical sciences, there is considerable flexibility in the choice of definitions. Try thinking naively about the following question. How would you mathematically define the notion of an information source? Several different answers to this problem have found widespread use, but Shannon came up with the most fruitful answer, leading to a plethora of deep results and a theory with rich structure that seems to reflect real-world communication problems. Shannon was interested in two questions related to communication of information over a channel. First, what resources are required to send information over a channel? Telephone companies need to know how much information can they reliably transmit over a given telephone cable. Quantum companies do need to know this too. Can information be transmitted in a way that is protected against noise in the communication channel? This is a really interesting question, and there was a paper that came out the other day that showed that there's a limit to how much noise you can remove from quantum communications and quantum data transmission, which means there's probably a fundamental level of, or fundamental limitation to how much error correcting codes can work and how much noise you can remove from quantum, which is not good for quantum. But I think it sort of makes sense. There's a lot of quantum fluctuation, and the whole idea of quantum mechanics and observer effect has spooked a lot of people for a long time. It doesn't make too much sense, and I feel like the ability for quantum computers to work requires really isolated conditions that are not given to errors and not given to success of scaling. Okay, Shannon answered these two questions by proving the fundamental theorems of information theory. The first theorem, I guess, he said Shannon's noiseless channel coding theorem. This quantifies the physical resources required to store the output from an information source. His second fundamental theorem is called the noisy channel coding theorem, which quantifies how much information it is possible to reliably transmit through a noisy communications channel. Again, we're dealing with a lot of noise in quantum. It's kind of one of the most fundamental things. This is why Nielsen is talking about this. To achieve reliable transmission in the presence of noise, Shannon showed that error correcting codes, this is what started the whole quantum rally, the Google error correcting code work. Before this, all these stocks were penny stocks. Shannon showed that error correcting codes could be used to protect the information being sent out. Shannon's noisy channel coding theorem gives an upper limit on the protection afforded by error correcting codes. Unfortunately, Shannon's theorem does not explicitly give a practically useful set of error-correcting codes. From the time Shannon's papers today, researchers have constructed better classes of error-correcting codes in an attempt to get closer to the limit set by Shannon's theorem. A sophisticated theory of error-correcting codes now exists, offering the user a plethora of choices in their quest to design a good error-correcting code. Such codes are used in a multitude of places like CDs, modems, satellite communication systems. So when you scratch a CD, the music still plays because there's a bunch of error-correcting codes, but scratch it enough and you will not be able to use it. Quantum information theory has followed similar developments. In 1995, Ben Schumacher provided an analog to Shannon's noiseless coding theorem, and in the process defined the quantum bit, or qubit, as a tangible physical resource. So 1995, qubit comes out as a term. However, no analog to Shannon's noisy channel, that's noiseless versus noisy, no analog to the noisy channel coding theorem is yet known for quantum information. Nevertheless, in analogy to their classical counterparts, quantum error-correcting codes have been developed, which allows quantum computers to compute effectively in the presence of noise, and also allows communication over noisy quantum channels to take place reliably. Notice this is in theory. At the time of this book, there's barely any quantum computers at all. Okay, classical ideas of error correction have proved to be enormously important. In 96, in developing quantum codes. In 96, two groups, 𝗏𝗏𝗏𝗏 and Shor, of course Peter Shor from Shor's algorithm, and Andrew Steen, another important name, discovered an important class of quantum codes now known as CSS codes, after their initials. This work has since, so C is 𝗏𝗏𝗏𝗏 and S is Shor and S is Steen, CSS codes. This work has been subsumed by the stabilizer codes, which are discovered by these other guys, including Shor. By building upon the basic ideas of classical linear coding theory, these discoveries greatly facilitated a rapid understanding of quantum error-correcting codes and their applications to quantum computing and quantum information. The theory of quantum error-correcting codes was developed to protect quantum states against noise. Like the biggest part of this game. The whole industry focused on this. What about transmitting ordinary classical information using a quantum channel? How efficiently can this be done? A few surprises have been discovered. In 92, Bennett and Wisner explained how to transmit 2 classical bits of information while only transmitting 1 quantum qubit from sender to receiver, a result known as superdense coding. Even more interesting are the results in distributed quantum communication. Imagine you have 2 computers networked trying to solve a particular problem. How much communication is required to solve that problem? Recently, it's been shown that quantum computers can require exponentially less communication to solve certain problems than would be required if the networked computers were classical. Unfortunately, there's no practical setting due to technical restrictions. A major challenge for the future of quantum computing is to find problems of real-world importance. This is like the critical thing here. This is basically the whole Baer thesis in one shot here. And I've talked to a lot of institutions and things like that. A major challenge for the future of quantum computing is to find problems of real-world importance. That's the key, real-world importance. That people will pay for, in other words. Real-world importance for which quantum computation offers a substantial advantage over distributed classical computation. That's the key question. Mike and Ike is the standard book in quantum computing. There's no newer book that people use, even though there are newer books that have been published. They're not used or taught with. Physics definitely hasn't changed. Although, look, there have been important findings in quantum computing since then. I believe Scott's one of the smartest people in the world. I've said this a few times. In my Forbes list, he's as rich as NVIDIA's CEO or something like this. And his blog's called 𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏 Landau. And this is the book, Quantum Computing Since Democritus. I highly suggest you get it. And Scott is a theorist. He's not a practitioner. He doesn't make quantum computers. But he wrote this book in 2013, and he recommended Mike and Ike for the basics of quantum computing. You don't want to read his book for the basics of quantum computing, but it's a wonderful book that I highly recommend. So what are these problems of real-world importance? Yeah, there's the famous saying, Stockfish, about Asimov and magic, by Asimov about magic. Technology, is indistinguishable from magic. I believe in quantum computing to some extent, but Scott is the same way. But, we got to be intelligent in how we think about it. Scott's also very bearish on D-Wave, by the way. Let's return to information theory proper. But yeah, the big question is, are there any problems of real-world importance that we need a quantum computer for? And my challenge to that question is, I don't think so. All right, let's keep reading. Let's return to the information theory paper. The study of information theory begins with the properties of a channel. In applications, we often do not deal with a single channel, but rather with networks of many channels. The subject of networked information theory deals with information-carrying properties of such networks and is a rich and intricate subject. And by contrast, the study of networked quantum information is in its infancy. Even for very, very basic questions, we know little about the information-carrying capability of quantum channels. Oh, I should also mention that the industrial field of quantum computing has had almost no progress since. My point in shorting quantum is very much that there are no practical or industrial applications. There's no actual problem that needs quantum computing. Several rather striking results have been found, but no unifying theory of networked information exists for quantum channels. One example of a network quantum information theory should suffice to convince you of the value that a good theory would have. Okay, this is an important concept. I think most people know this, but maybe 𝗦𝗛𝗡𝗦 doesn't. But this is bullish for you, 𝗦𝗛𝗡𝗦. This is one of the things that got me interested in this field. Imagine that we are attempting to send quantum information from Alice to Bob through a noisy channel, a quantum channel. If that channel has zero capacity for quantum information, then it's impossible to reliably send any information from Alice to Bob. Instead, imagine that we consider two copies of the channel operating in synchrony. Intuitively, it is clear and can be rigorously justified that such a channel also has zero capacity to send quantum information. However, if we reverse the direction of one of the channels, it turns out that sometimes we can obtain a non-zero capacity for the transmission of information to Alice and Bob. Counterintuitive properties like this illustrate the strange nature of quantum information. Better understanding these networks is a major open problem for quantum computation and information. Let's switch fields one last time. So we've done three different fields. This is the fourth. Moving to the venerable old art and science of cryptography. Cryptography is the problem of doing communication or computation involving two or more parties who may not trust each other. The best known cryptographic problem is the transmission of secret messages. Before we get there, I want to show you this thing. If you have two very noisy channels with zero capacity running side by side, the combined channel is zero capacity. But if we reverse one of the directions, we still have zero capacity. But in QM, reversing actually allows us to send information. Okay, secret messages. Suppose two parties want to communicate in secret. You may want to give your credit card number to a merchant, but you don't want a third party like me intercepting your credit card number. This way, the way we do this is a cryptographic protocol, and most the biggest difference or systems that we're going to look at are private key and public key systems. Well, private key requires you share a key previously, which only the two parties know. The point is that the key is used by Alice to encrypt the information she wants to send to Bob. And then Bob now recovers the initial information, but the information is dependent on the private key. So Bob needs to know the private key. Unfortunately, this is not a great system. The most basic problem is, how do you give the key to somebody? Key distribution problem is just as difficult as the original problem of communicating in private. A third party may get the key. So one of the earliest discoveries in quantum, and this is very bullish as well and very important, was quantum mechanics can be used to do key distribution in such a way that Alice and Bob's security cannot be compromised. This procedure is known as quantum cryptography or quantum key distribution. You might see the abbreviations QKD. The basic idea is to exploit quantum mechanical principle that observation in general disturbs the system being observed. This is a key idea. in quantum mechanics and kind of makes quantum computing impossible, according to some people. So if there's an eavesdropper listening in as Alice and Bob transmit their key, the presence of the eavesdropper will be visible as a disturbance of the communications channel. So this is the key idea of quantum communication, that you can get a provably secure line. And of course, this is somewhat interesting to governments. And this is, one of the most fundamental principles. So Alice and Bob can throw away those bits while the eavesdropper was listening and start over. The first quantum cryptographic ideas were proposed by Stephen Weisner in the late 1960s, but were not accepted for publication. This is an old field. In 84, Bennett and Brassard, this is a BB84. So this is called BB84. We looked at this. Do you guys remember us looking at this? This is when we were looking at ion queues. So since 1984, BB84 has been out. So they built on Weisner's work, and they proposed a protocol using QM to distribute keys without the possibility of any compromise. This has been used for decades, and it's not a big field. So IonQ kind of bought the leader in the field. They won't tell us how much revenue that company had. So they're buying the company to make up for the revenue that they don't have from their normal business. This is the key part, is the public key crypto system. Public key crypto systems don't rely on sharing the key in advance. Instead, they publish a public key. So you use the public key to encrypt a message, but a third party cannot use the key to decrypt. This is basic RSA, ECC, etc. Strictly speaking, we shouldn't say cannot, because the encryption transformation is chosen in a way that it's extremely difficult but not impossible to invert, given the knowledge of the public key. The secret key, the private key, enables him to easily perform the decryption, but it's not known to anybody else. So you can be confident that even though the encrypted message is public and the public key is public, you cannot decrypt the message. Nobody has that kind of computational power. It would take you millennia or billions of years even to decrypt some of these messages. We talk about this sometimes in my Discord. There's a guy that claims the NSA can decrypt RSA 2048, which I strenuously disagree with. So public key cryptography did not achieve widespread use until the very, very famous Whitfield Diffie and Martin Hellman and Ralph Merkle created the Merkle tree, revolutionized the field of cryptography. And then Rivest, Shamir, and Edelman developed RSA cryptosystem. This was one of the most important advances in all of humanity, I would argue. Rivest is an MIT professor, still teaches cryptography, and he's of course he's the R in CRPS, or is it CRPS? The famous algorithms book. So this is really interesting and relevant, very relevant to quantum, okay? Rivest, Shamir, and Edelman, sort of MIT guys, developed the RSA cryptosystem. It offers a balance of security and usability. In 1997, it was disclosed that all of these ideas, look at this, they're already invented in the late 60s and 70s by the British NSA, GCHQ. GCHQ. So the key to crypto systems, public key crypto systems, is that it's difficult to invert the encryption stage if only the public key is available. Inverting it is very close to factoring. So the belief is that factoring is hard to solve on a classical computer. But Shor's algorithm on a quantum computer could be used to break RSA. This is a really revolutionary idea. That's why Peter Shor, also an MIT guy, has a major name now. So other algorithms could be broken if you solve the discrete log problem, and you can do that with Shor's. So a lot of people are excited about breaking cryptographic codes with quantum computers. And this is where I think is the main industry that'll use quantum. I don't think it's good for virtually anything other than code breaking. But I also don't think we're going to see it soon. So when it does happen, it's maybe $1 billion market. I don't think that the code breaking market's that big. We've been looking at historical antecedents for quantum. Of course, the field has grown and matured, sprouted subfields, and there's a lot to cover here. But let's talk about the field of quantum entanglement, okay? And I think we're starting to get to the fundamentals of quantum computing here. This is a 700-page book, so pace yourself. Yeah, it's not hard to shift to quantum-proof encryption. Code breaking is suitable for a quantum. Great question.
in short, quantum is very good. Large combinatorial problems, so numbers that get too large, quantum is extremely good at solving those problems, but it's not good at storing things. For example, it's not good at retrieving and outputting things easily. It's not good at creating lots of data, for example. So you couldn't really use it with AI or something. You can't load terabytes of data into a quantum computer. There's no quantum memory at all. But let's talk about some of these details. Quantum entanglement. Entanglement is a uniquely quantum mechanical resource. I want you to think about this concept of a resource. Keep that in the back of your head for a minute. It's a resource that plays a key role in many of the, pretty much all of quantum computation. Entanglement is the iron to the classical world's Bronze Age. I like that. There's been a tremendous effort to understand entanglement as a fundamental resource of nature. It's just as important possibly as energy, information, entropy, or any other fundamental resource. Maybe strong force, weak force, electromagnetism. Although there's yet no complete theory of entanglement, some progress has been made in understanding this strange property of quantum mechanics. Studying entanglement will yield insights that may facilitate quantum computers. All right, future directions. We've looked at some of the history, present status of quantum. What is the future? What can quantum computation offer to science, technology, and humanity? What benefits does quantum computing confer upon its parent fields of computer science, information theory, and physics? What are the key open problems of quantum? I'll make a few brief remarks here. Quantum computing has taught us to think physically about computation. I would dispute that. And we have discovered that this approach yields many new and exciting capabilities for information processing and communication. Computer scientists have been gifted with a new and rich paradigm for exploration. In broadest terms, we have learned that any physical theory, not just quantum mechanics, may be used as the basis for a theory of information processing. I would argue we knew that. The fruits of these labors may one day result in information processing devices with capabilities far beyond today's systems, with benefits and drawbacks for society as a whole. Quantum computation certainly offers challenges to physicists, but it's perhaps a little subtle what quantum offers to physicists in the long term. We believe that just as we have learned to think physically about computation, we can also learn to think computationally about physics. Whereas physics has traditionally been a field focused on understanding elementary objects and simple systems, many interesting aspects of nature arise only when things become larger and more complicated. Chemistry and engineering deal with that complexity to an extent, but mostly in an ad hoc way. One of the messages of quantum computing is that new tools are available for traversing the gulf between the small and the relatively complex. Computation and algorithms provide systematic means for constructing and understanding such systems. Applying ideas from these fields is already beginning to yield new insights into physics. It is our hope that this perspective will blossom in years to become a fruitful way of understanding all aspects of physics. Okay, this is where the book really starts. That was the introduction. Now we get started in the meat of the matter. Chapter 1.2, Quantum Bits. Pay attention. If you haven't been paying attention, it's time to pay attention. The bit is the fundamental concept of classical computation and classical information. We all know that. Quantum computation and quantum information are built on an analogous concept, the quantum bit, or qubit for short. In this section, we introduce the properties of single and multiple qubits, comparing and contrasting their properties to those of classic bits. This is going to be a real uphill climb real fast, guys. Be careful. What is a qubit? We're going to describe qubits as mathematical objects with certain properties. But hang on, you say. I thought qubits were physical objects. It's true that qubits, like bits, are realized as actual physical systems, and we're going to talk about that in detail, how we make this connection between the abstract mathematical point of view and real systems. But for the most part, we're going to treat them as abstract mathematical objects. The beauty of treating qubits as abstract entities is that it gives us the freedom to construct a general theory of quantum computing, which doesn't depend on any specific system for its realization, right? We don't need to worry about whether it's D-Wave or Rigetti or IonQ that we're using, the leaders in the field. What then is a qubit? All right, just as a classical bit has a state, either 0 or 1, a qubit also has a state. Two possible states for a qubit are the states 0 and 1, which, as you might guess, correspond to the states 0 and 1 for a classical bit. So far it sounds like the same, right? Notation like this is called the Dirac notation. And we'll be seeing it often, you bag holders, as it's the standard notation for states in quantum mechanics. Now, you already know something you didn't before. Congratulations. This is the Dirac notation. The difference between bits and qubits is that a qubit can be in a state other than 0 and 1, okay? A lot of people don't know this. A lot of people don't understand this. This is a pretty complicated idea. It's going to be simple for you to understand in a minute. But this is something a lot of people don't know. Even the most fundamental thing about quantum, and oftentimes they'll missay this. You'll see this in the media all the time. So I want you guys to understand this once and for all. The difference between bits and qubits is that a qubit can be in a state other than 0 or 1. A lot of people say that the difference between a qubit and a bit is that it's either in 0, 1, or both, which is not right, and is a fundamental misunderstanding of quantum. It is possible to form linear combinations of states, which are called superpositions. Okay, so we've talked about linear combinations in this YouTube many times, right? We talk about linear combinations. We did this just yesterday, right? Do you guys remember? These are the factors of a factor model that explain, and etc., right? That explain the stock price change. You have this coefficient that represents an amount, and you have a factor that represents certain things, like, say, country, industry, momentum, whatever. There's hundreds of them. So this is a linear combination, right? Anybody who's done not just linear algebra, but any kind of math at all understands this. This alpha is a proportion, right? It's like a weighted average. And here's this state. We know the state is 0. It could be on or off, right? So this is off. And we'll have this added to beta, which is a proportion of how often it's on, right? Just like a transistor or a switch or a light bulb, that's a linear combination. But what does it mean to be in a combination of these states? Because we often think something's either on or it's off, right? How could it be kind of off and kind of on at the same time? So A and B are complex numbers. What's a complex number? Do you guys know? It's a number that has an I component, right? The I component could be non-existent too, by the way, but 6i, right? I is square root of -1. So this is just the basics, right? We're not going to get into the advanced stuff. One guy, if you wanted to get it more into this, to watch is Scott Aaronson, John Preskill. There's many others that you can follow who, it's not easy to make this stuff simple. Sometimes the best teachers are not necessarily the best practitioners, by the way. The numbers A, alpha, and beta are complex numbers, but we don't lose much by thinking of them as real numbers. And I kind of want you to think of them as real numbers. Back up here so you can understand that, like, maybe this is 70% 0 or off. And this is 30% on. Could that be the case? That's what I want you to really understand here. This is the beauty of quantum. Do you guys get it so far? That unlike something that's on or off, there's no coefficient for a bit. It's either on or off. So you got 0. What's a string of bits look like? 0, 1, 0, 1. Does anybody know what this number is? This is 1, the 1's column, the 2's column, and the 4's column, right? So this is 5. What if I add a 1 over here? It's up 33%, actually. Put another way, the state of a qubit is a vector in a two-dimensional complex vector space. Did I lose anybody? I'm going to ask ChatGPT. Can you make this sentence much simpler to understand? A qubit state is like an arrow in space with two directions.
using complex numbers. Makes it real simple. How can an arrow have two directions? A qubit state is just a pair of numbers, but these numbers can be complex. They could have an imaginary component. So why did you say vector space just to confuse long qubit? Fair enough. Vector space is just a fancy math phrase meaning a collection of things you can add together or multiply with, like arrows, coordinates, or even pairs of numbers. A qubit state is simply described by two complex numbers. That's it. Long qubit indeed. Oh, GPT likes qubit. The special states 0 and 1 are known as computational basis states. So if you study any other math or physics, basis is kind of like, what your unit is, like I or J or something. These basis states form an orthonormal basis for the vector space. Let's break that down super simply. The special states 0 and 1 are just two basic states to describe qubits. We know that. They're special because they're different from each other, and they form the simplest possible set of states. They can describe every other state. So they're like the reference states. Every qubit state is built from these basic states. Orthonormal just means they're clearly different and easy to tell apart. Sometimes, the word ortho, maybe we should just leave it alone. Bill Gates famously thought the internet wouldn't be very, very successful. Ortho comes from the Greek straight or correct. So when we say orthosteric, we mean this receptor site that's normally used. When we say allosteric, we mean somewhere else. So for qubits, ortho means at right angles. So it's orthogonal. You've heard that word sometimes. People kind of overused it for a while. So they're the orthonormal basis. Between these two, you can get the entire vector space. So this is like linear algebra, right? Okay, we can examine a bit to determine if it's in the state 0 or 1. For example, computers do this all the time when they retrieve the contents of their memory, right? If you store this number, computer sort of will translate that from binary. Again, we have 1, 4, this is 8 and 16. So this is the number 21 in memory. And maybe that's 21 pixels to create a blue dot or something, 21 pixels to the left or to the right. This is how computers store things. And the computer has to go check what bits are stored. Is it a 1? Is it a 0? And a mistake could be rather problematic, which is why we need high fidelity. We'll get to that later. None of these quantum systems have high fidelity, unfortunately, so they're not usable yet. Rather remarkably, okay, so computers do this every second, right? They do this every minute, every millisecond, every nanosecond. They're looking at memory and determining what state are these bits in. And there's lots of bits. They form bytes, and then we have megabytes and gigabytes and terabytes, and even petabytes and exabytes. Rather remarkably, we cannot examine a qubit to determine its quantum state. So we cannot tell what the values of alpha and beta are. Instead, quantum mechanics tells us that we can only acquire much more restricted information about the qubit state, the quantum state. When we measure a qubit, we will get either 0 or 1. And the probabilities, we square it for a specific reason, but the probabilities have to sum to 1. Anyone know why we square it? You can also note that you can interpret this as the qubit state is normalized to length 1. What does that mean? What does this look like? What equation does this look like? Thus, in general, a qubit state is a unit vector with a two-dimensional complex vector space. Okay? This dichotomy between the unobservable state of a qubit and the observations we can make lies at the heart of quantum computing. In most of our abstract models of the world, there's a direct correspondence between elements of the abstraction and the real world. The architect's plans for the building are in correspondence with the final building. The lack of this direct correspondence makes it difficult to have intuition about quantum. But there is an indirect correspondence. Qubit states can be manipulated and transformed in ways which lead to measurement outcomes which depend on the properties of the state. So the quantum states have real experimentally verifiable consequences, which we'll see is essential to how quantum computing works. So the ability for a qubit to be in a superposition state is counter to common sense.
We don't understand the physical world around us, but the quantum world is much different from the physical world. You know, if any of you guys watched my lectures in chemistry, I did a whole 15 video series or something like that on general chemistry. And we talked about the quantum world and how at very small sizes, classical physics tends to break down. A classical bit is like a coin. It's either heads or tails, right? But for imperfect coins, there may be intermediate states like balanced on an edge, but we basically disregard that and keep the abstract state. A qubit can exist in a continuum of states between 0 and 1 until it is observed. Pretty wild stuff. Let's emphasize again, when a qubit is measured, it only can give 0 or 1 as its result, but it's probabilistic. So here's an even qubit state. Why does it look like this? Well, we have to do the square root of 1/2, but this is what it looks like. So normally I would tell you, well, if I wanted to do a 50-50, well, that's pretty easy, right? I can just do 0.5, and I could do 0.5 of this guy, right? 50-50. Just like if I wanted to average a moving average of two prices, this is how I do it. I don't even need the coefficients, to be honest. But because 50% is 1/2, and because I have to take the square root of this, it's best to do, you know, we usually try to simplify it if we can, but this is equal to this. So we just square root of 1 is 1. And that's how we have the square root of 1/2 plus the square root of 1/2 when squared will equal 1. So these are the probabilities. So this is a 50% of the time when I observe this guy, okay, I'll see 0. I'll see the off state. And the other 50% of the time when I observe it, I'll see this. I'll see the on state. So this is a 50-50 coin flip in quantum world. Pretty cool, because as we may know from computing, it's kind of hard to do random numbers. Now, these are true random numbers, and some people think one of the advantages of quantum computing is that you can get true random numbers, which is true. That is one of the advantages. And this state has often got an abbreviation. We use it so often. It's just called this. All right, so when we measure this, half the time we're going to get a 0 and half the time we're going to get a 1. So it's kind of like flipping a coin. You get heads and tails. And slowly but surely, it'll sort of approach 50-50. Qubits are real. Their existence and behavior has been validated. And many systems can be used to realize qubits. There's ion traps, which Alejandro apparently, he knows those are the best ones. There's superconductors. There's neutral atoms. There's lots of ways. There's Majorana. But, you know, we got to listen to Alejandro because he knows it's the ion trap, right? To get a concrete feel for how qubit can be realized, it's helpful to put a list of ways this realization may occur, okay? The simplest way is polarization. Two different polarizations of a photon, okay? Let's keep this in the back of our mind because we might go back to this. The alignment of nuclear spin in a uniform magnetic field, well, that's called NMR. We already have NMR. It's not a big market. This is a major book. It's the book, canonical book in the field by Michael Nielsen and Isaac Chung. Two states of an electron orbiting a single atom. Let's look at that. Here's one state where the atom, we'll call it, is in 0 position, or the electron is in 0 position. And another state where it's in 1 position. Okay? The electron is either in the ground state or in the excited state. And there's no in-between state. That was an important finding. That's when we start saying the word quanta. It's discrete, not continuous. By shining light on the atom with the right amount of energy for the right time, you can move the electron from 0 to 1. It'll eventually drop from 1 to 0. But interestingly, we can also put it in superposition where it's halfway between 0 and 1. But what does that mean? You know, how do we interpret that? Is it really halfway between 0 and 1? No, it's probabilistic. Half the time when we observe it, it'll be in 0. Half the time when we observe it, it'll be 1. So a good question from the community, Ulysses asks, what do you make of the intelligence community, store now, decrypt later? So this is the idea that the NSA and the Chinese equivalent is basically hoovering all of our information from hacked lines and hacked communications and just downloading the whole internet, especially certain targets, like maybe a diplomat's traffic or something like that. And basically saying, I can't decrypt this right now because I don't know how to invert, a private key. But when quantum comes around, I'm going to decrypt it. Well, the problem with that is when quantum comes around 20, 30 years from now, we'll be able to decrypt old information. And right now, a lot of the best information is already being stored on post-quantum cryptography. And furthermore, a lot of the best information is kind of well known already. One of the things about espionage is that so much of what we learn in espionage is already known to everybody, and that signals intelligence like this, well, there's a lot of ways to get signals intelligence. You can do it with microphones. You can do it with other kinds of computer hacks. You don't need to descramble an encrypted line. It's maybe 5% of the way. In fact, the WikiLeaks cable releases, I remember cooking up some popcorn and saying, oh man, they're going to release diplomatic cables. This is crazy. All the state secrets are going to come out. Wow. And then when they came out, nobody thought they were interesting. There was nothing in there that was fascinating. The Chinese said, one Chinese ambassador was caught saying that Chinese economic numbers are fake. Well, everyone knew that. Another diplomat said, well, the Russians, they're all a bunch of drunks. Well, that's what people thought anyway. There was nothing that was really that secret that was being communicated. Of course, these diplomats, sometimes heads of state, they didn't want to communicate their secrets, right? They were really embarrassing. But they also weren't saying anything that interesting. So if somebody read your communications or my communications, well, you'd see what I'm saying to my friends. You can guess, right? Talking about money, it's all the stuff you would imagine, and none of it's that interesting. And certainly none of it is worth paying billions and billions and billions for. Now, if you're a spy, or a spy hunter, yeah, I'd want to know the list of spies that might be in the FBI, in the CIA. Yeah, I might want to know military plans. But you still have to know where to look. The internet's a big ocean. So you kind of have to know where to look. And by the time we have quantum, all that information is going to be old and useless. I think that the idea that the NSA really wants this is a little bit, if you actually talk to some people in these circles, I'm not sure they're that useful. I'm not sure the NSA is going to buy a lot of this stuff. And the NSA budget is not that big, believe it or not. And some say they already have it. I disagree. There's backdoors. There's some backdoors. So you often don't need it. What you can accomplish with normal side channel attacks without a quantum computer, what you could accomplish with a quantum computer, right? So what's a side channel attack? Anybody know? Let's ask ChatGPT. Give me a good example of a side channel attack. Classic example is a timing attack. Imagine a secure login system. You type in your password, and it's going to try to it's going to check your password, right? And your password is wrong. The first character doesn't match, so it says this isn't your password, right? If you try testing passwords and one of the passwords takes way longer, I'm talking milliseconds, but it takes twice as long to determine that's the wrong password. You say, wait a second, why is the computer taking longer to determine? Maybe it's closer. I'm closer to the password than it looks. Yeah, fan speed, electricity, these are all side channel attacks. Everything is quantum. We need it now. The White House needs it. We need to spend more money on quantum. A great deal of attention has been given to the meaning or interpretation that might be attached to superposition states and of the probabilistic nature of these observations, but we're not going to concern ourselves with that. Our intent is to develop mathematical and conceptual pictures which are predictive. Let's look at the following geometric representation. I think this is where we lose everyone. Does anybody know this equation? E to the I, that should already make you crazy, gamma times cosine of theta over 2. It kind of looks similar to the one we looked at before, right? Of the 0 position plus e to the I gamma of sine
of theta over 2 of the 1 position. Notice we have this e to the I outside and inside. This isn't exactly quantum mechanics. So apparently we can factor this out. So now we're down to just this. And again, this looks pretty similar to the one we looked at earlier, except we have got cosine of this as our coefficient. And here we've got sine of, it looks similar to that, but it's cosine of, this is the coefficient. This is the coefficient here. I would say the whole term is coefficient, but you could argue that this is the coefficient as well. So we can write it this way instead, and that theta and phi are points on the Bloch sphere. Here's the Bloch sphere. This is an elementary concept in quantum computing. So I want you to, if you could take away anything from this video, you say, I now know what a qubit is, sort of. We haven't really gotten into it, have we? Linear combination of states. I use a mouse. And then I have a tablet here somewhere. I gotta go find it. And then, oh, okay. Did you see this thing where the average physicist IQ is 30 points ahead of other majors? It's like 130. It's wild. Smartest people in physics. That's why I couldn't cut it. Bloch sphere representation of qubits. So this is the Bloch sphere. So anything, if anything you take away here is you could say that, you know, Shkreli showed you the Bloch sphere. So here's the Bloch sphere. Doesn't look like as much of a sphere as we'd like it to be, right? We don't get the curvature just right. But that's a sphere. And so we have a z direction, right? So these numbers are points, unit sphere. So when you learn trigonometry, you learn about what? The unit circle, right? And you learn how to do your little trigonometry. Well, this is a unit sphere, right? And we are going to use polar coordinates. So this sphere is really useful for visualizing the state of a qubit. You're going to see this a lot, the Bloch sphere, and it's a really good tool mentally to kind of think about quantum. And so a lot of the times when we do gates in quantum, we're just moving it on the Bloch sphere. We might be rotating it or flipping a sign, right? So the Bloch sphere is B-L-O-C-H. It was Seymour Bloch, physicist, but I don't remember. And so all these operations in quantum are kind of like very nice to visualize on the Bloch sphere. But there is no Bloch sphere for a lot of different sort of, you know, the abstraction reaches an end at some point. Felix Bloch, thank you. So how much information is represented by a qubit? This is a really fun idea. There's an infinite number of points on the unit sphere, right? Just like there is on the unit circle, right? Reals are infinite. In fact, there's a cardinality, as you guys may know, from what? From 0 to 1. Which is bigger? The amount of numbers from 0 to 1 or the amount of integers from 0 to infinity? Which is bigger? You guys know? Let's ask Chat, see if ChatGPT knows. What is bigger, the amount of reals from 0 to 1 or the amount of integers from 0 to infinity? Light work for French, for the Polak. What's up? There we go, pretty simple. There you go, 𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏
Ben answered 5 times. So this is Aleph null. Aleph null and Aleph, is this Aleph 1? What's the size of the uncountably infinite? There are, just like in complexity where you can't always put things in the P or NP box, sometimes you can't put things in the Aleph box either. So there's a lot of open questions on the continuum. This is the biggest one, the continuum hypothesis. Is the size of reals Aleph 1? And this is one of the biggest questions in math. Hilbert was a famous mathematician. He said that once Cantor came up with the Aleph system in the diagonalization argument, that nothing could drive us from Cantor's paradise, is what he said. So I made okay, so there's an infinite number of points on the sphere, right? So you could store the entire text of Shakespeare in the infinite binary expansion of theta. Well, between 0 and 1, you could store any infinite expansion, but you lose precision, right? And this was the old Sagan joke
Where's 𝗤𝗡𝗏𝗧𝗏? This is the old Carl Sagan idea that if you ever watch the great film Contact, one of my favorite movies, well, the idea in the book is that if you calculate pi out, and this is not true, by the way, but some of you will probably think it's true. 𝗤𝗏𝗏𝗧𝗏 will probably think it's true. If you calculate pi out, you of course get the normal digits, right? But guess what? At some point, pi is not random. So after a while, you get a string of zeros. Okay? And those zeros tell you that the instructions for the universe are coming next. And it sort of gives you this binary of, how to build space travel or something. And it's code from the creator of the universe. It's in there. It's all in pi. I don't know. And so it's a great movie. In the movie, they did something different. They said that, right? Well, maybe it's there. Maybe we keep dividing. We might see the code. In the movie, they have a signal that's different sounds, and they listen to the sounds. They say, what are those sounds? And they realize that they're listening to prime numbers. It's pretty spooky, actually. This is spookier. Although pi is a little spooky, too. Is 27 a prime? Anybody know? The behavior of a qubit, when observed, we're only going to get 1 or 0, so it doesn't help us to store the entire corpus of Shakespeare, does it? Measurement changes the state of a qubit, collapsing the superposition of 0 and 1 to a specific state. So if we measure it and it gives 0, the post-measurement state of the qubit is 0. Why does this type of collapse occur? Nobody knows. We just don't know. This is a fundamental postulate of quantum mechanics. God made it that way. We don't know. That's about all we know. Well, that's about all we've got. What is relevant for our purposes is that from a single measurement, one obtains only a single bit of information about the state of the qubit. So are we losing information? Is information conserved or destroyed? Seems like it's getting destroyed, isn't it? Isn't it? What does it say about entropy? Right? Isn't entropy supposed to go up in infinity? Is entropy information? Or is the opposite? We're taking information, we're creating randomness. So only if infinitely many identically prepared qubits were measured, one would able to measure the coefficients, alpha and beta. Only if infinitely many identically prepared qubits could we measure the state. Why? Because we're probabilistically sampling it, right? But an even more interesting question, how much information is represented by a qubit if we do not measure it? This is a trick question. Because how can one quantify information if it cannot be measured? There is something conceptually important here, because when nature evolves a closed quantum system of qubits, not performing any measurement, she apparently does keep track of all the continuous variables describing the state, like alpha and beta. So this is the important question. We have all these quantum mechanical processes going on. How can nature as a computer be holding all this information? It's a lot of information. It's a shadow realm. Yeah, we're going to talk about Bell. Bell comes into play quite a lot. In fact, in Aronson's book, Bell is ever present. So the state of a qubit has tons of hidden information. We'll see shortly that this potential amount of extra information grows exponentially with the number of qubits. So if you understand this hidden quantum information, you'll understand quantum computing. And this is why this hidden information that we can't observe, right? We cannot observe this. This is what lurks. This is what makes quantum computing possible. When we observe it, it collapses. It's gone. It goes to 1 or 0. But when the qubits are in their quantum state in superposition, they can contain an infinite amount of information. So then the book goes to multiple qubits, and it gets very hard to understand from here. Here's EPR, which you guys are talking about in chat, John Bell. Even just the next 2 pages are very, very hard to understand. And then some pages after that are as well. Now, some of you are smarter than me, although the probability of that is exceedingly low. Some of you are, because there's selection bias here. And this is Mike and Ike, the one and only. So, you know, some of you can read this and I can't, and that's great. But I didn't do physics. Michael Nielsen's famous book. If you want to be a quantum computing expert, you can read that. You can read all the stuff about archive, but it works the same way in biotech. Do you want to read all the stuff in biotech?